Here's every major wood joint explained and exactly what each one is for. Butt joint. Two pieces meet, end to face or end to end, and nothing about the geometry helps you. There is no interlock, no mechanical resistance, nothing but glue and whatever fastener you drive through it. That matters more than it sounds, because the end grain of a board drinks glue like a bundle of straws. Those open pores wick the adhesive away from the joint line before it can cure, and you end up with a starved bond that looks fine and fails under load. The fix is called sizing. Brush a thin coat of glue onto the end grain, wait a couple of minutes for it to begin setting and plug those straws, then apply a full coat and clamp. Do not thin it with water. Yellow glue is already about 40% water and soaks in perfectly well on its own. Even then, treat the fastener as the strength and the glue as insurance. It is the fastest joint there is, and in a shop jig, a shelf cleat, or a shipping crate that is the right trade. In a chair leg, it is a failure waiting for a date. Pocket hole joint. This is the butt joint with the problem engineered around. A stepped bit drills a shallow angled tunnel into one workpiece, and a self-tapping screw runs through it at roughly 15 degrees into the mating piece. The angle is the whole idea. It converts what would be a weak end grain pull into a clamping force that pulls the two faces tight and holds them there while the glue cures. And the screw threads bite into long grain rather than end grain, face frame work, cabinet boxes, quick shop furniture. The limits are honest ones. The hole is visible unless you plug it. The joint resists shear well and racking poorly, and the screw is doing work that a shoulder should be doing in anything that gets levered on. Rabbet. A rabbet is an L-shaped recess cut along the edge or end of a board. One cut, two gains. You get a shoulder that registers the mating piece and locates it without measuring, and you roughly double the glue surface compared to a plain butt, because now a face is meeting a face instead of an end meeting a face. This is the back panel of a cabinet, the case corner of a drawer, the seat of a glass in a door frame. Cut it a hair deeper than the mating stock is thick and plane the proud edge flush afterward. Chasing an exact fit on the saw costs you an hour and gains you nothing. Dado and groove. Same cut, different direction. A dado runs across the grain, a groove runs with it, and both are three-sided channels that capture a mating piece on two faces. That capture is what makes a bookshelf instead of a pile of boards. The load on the shelf pushes down into the bottom of the dado, and the two cheeks stop the shelf rolling forward. Cut it 1/3 the thickness of the stock deep. On 3/4 inch material that is a 1/4 inch. Half the thickness is the absolute limit, not the target, because past that you have removed more than half the cross-section of the side panel and it becomes the weak point instead of the joint. The stopped dado is the version worth learning. Stop the cut short of the front edge and notch the shelf to match, and the joint disappears from the outside. Half lap, two pieces cross, and you remove half the thickness from each so they nest flush. The result sits in one plane, which is the point, and it gives you a large flat glue surface of long grain against long grain, which is the strongest bond wood can make. Cross laps for frames and torsion boxes, end laps for corners, dovetailed laps where the joint has to resist being pulled apart. The weakness is what you took away. Each piece is half as deep as it was, so bending strength drops sharply. Do not put a half lap in the middle of a span that carries weight. Bridle joint. Think of it as the half lap grown a third dimension. One piece gets a slot cut in its end, the other gets a tenon cut to fill it, and the joint locks in two planes instead of one. Corner bridles for workbench frames and door frames, T-bridles where a rail meets a stile mid-span. It is the joint to reach for when you want mortise and tenon strength and you do not want to chop a mortise because a bridle can be cut entirely on a table saw with a tenoning jig. The trade-off is that both cheeks are visible from the outside on two faces. That is either honest joinery or a flaw, depending on the piece. Mortise and Tenon. This is the one everything else is measured against. A rectangular hole, the mortise, and a rectangular tongue, the tenon, sized to fill it. What makes it strong is not the glue area alone, it is the shoulders. The tenon shoulders bear against the face of the mortised piece all the way around, and that is what stops the joint racking when someone leans back in the chair. Rule of thirds. The tenon should be roughly 1/3 the thickness of the stock, so the two mortise cheeks each get 1/3 too, and no part of the joint is the obvious weak one. Cut the mortise first, always, then fit the tenon to it. It is far easier to shave a tenon than to widen a hole accurately. Variants worth knowing. The haunched tenon, which keeps a groove filled at the end of a frame. The through tenon, which exits the far side and can be wedged. The drawboard tenon, where an offset peg pulls the shoulders tight permanently and needs no clamps at all. Dowel joint. Round tenons, in effect. Holes are bored in both pieces, and hard wood pins bridge them. Done accurately, it is strong, invisible, and fast. The word doing the work is accurately. Every dowel has to line up in 2 planes at once, and a doweling jig is not optional unless you enjoy assembling furniture that will not close. Use fluted dowels, not smooth ones. The flutes let trapped glue and air escape as the pin seats. And without that escape route, you are hydraulically splitting the piece you just drilled. Biscuit joint. A slot cutter swings an arc into both mating edges, and a compressed beech oval goes in with glue. The biscuit swells as it absorbs moisture from the adhesive and locks in the slot. Understand what this joint is for. It adds very little strength. What it adds is alignment, and on a wide panel glue up where 4 boards have to come out of the clamps in one flat plane. Alignment is the entire problem. The slot is longer than the biscuit on purpose, which gives you side-to-side adjustment while the glue is open. Use it for panels, carcass alignment, and mitered corners that need registration. Floating tenon. Same idea as a biscuit, executed as real joinery. A slot mortise is cut in both pieces and a separate loose tenon spans the gap. You get genuine mortise and tenon strength without cutting a tenon on the workpiece, which means no shoulder to fit and no risk of trimming a rail too short. It is faster than a traditional mortise and tenon and nearly as strong. And the honest caveat is that a loose tenon has 2 glue lines where an integral tenon has 1. In practice, that has never been what failed. Tongue and groove. A tongue on one edge, a matching groove on the other, repeated across a run of boards. The joint locates every board flush with its neighbor, and critically it lets the boards move. Wood expands and contracts across its width with humidity, and if you glue a wide floor or a panel rigid, it will split itself. Tongue and groove holds the surface aligned, while allowing each board to slide a little inside the next. Floors, paneled doors, cabinet backs, exterior cladding, glue it only where you actually want it fixed. Mitre joint. 2 pieces cut at complementary angles, usually 45 degrees, so the corner shows no end grain at all. It is the best looking corner in woodworking and one of the weakest because both mating surfaces are end grain and end grain glues badly. It needs reinforcement, and the reinforcement is also the decoration, splines set into kerfs across the corner, keys, dowels, or a biscuit buried inside. Accuracy is brutal here. An error of 1/2 degree shows as a visible gap, and it shows 4 times over on a picture frame because the error compounds around the loop. Box joint. Interlocking square fingers, cut on a jig, alternating between the 2 pieces. Every finger presents 2 long grain faces to the mating piece, and with 8 or 10 fingers per corner, that adds up to an enormous glue area. That is where the strength comes from, not from interlock. It is mechanically simple, repeatable, and the jig is a Saturday project. Drawer boxes, tool chests, shop storage. It will not pull apart under any load a drawer will ever see. Dovetail. The fingers get angled, and the joint changes character entirely. Because the tails are wider at the end than at the base, The joint is mechanically locked in one direction. Pull on a drawer front all you like, and the geometry itself refuses. This is the only common joint that resists tension without relying on the glue. Through dovetails show on both faces, and are the honest, visible version. Half-blind dovetails stop short of the front, which is why a traditional drawer front looks solid from the outside while the sides are dovetailed in behind it. Cut angle is convention, not physics. Roughly 1 in 6 for softwood, 1 in 8 for hardwood. Too steep and you create short grain at the tips of the tails that snaps off during assembly. Scarf joint. This one solves a different problem. Not how to join two pieces at an angle, but how to make a long piece out of short ones. Both ends are cut at a long, shallow taper, often 1 in 8 or shallower, and glued face to face. The shallow angle is what converts an end-to-end joint, which is nearly unglueable, into a long grain to long grain joint with a lot of surface, and the ratio is the whole joint. 8-to-1 recovers roughly 75% of the strength of solid timber. 12-to-1 gets you to about 85. Traditions set it by the job. 4-to-1 for planking, 6-to-8 for a keel, 12 for a spar that has to bend without letting go. The rule is that longer is stronger, and the length of that overlap matters far more than the glue you choose. So how do you pick? Ask 2 questions. Which way will this joint be loaded, and does anyone need to see it? If it is pulled apart, dovetail. If it is racked, Mortise and Tenon, or bridle. If it carries weight downward, Dado. If it needs to be flat and fast, pocket hole or biscuit. If it must be invisible, mitre it and hide the reinforcement inside. Everything else is preference, and preference is allowed once the load is handled.